Hello everyone. So today this is the third live session for the course Physics through Computational Thinking. So I am Bhaskar there, and I am going to discuss about some example, how to solve them in Mathematica and how to plot. Basically, this session will be focused on the technical aspect of the Mathematica using. So I will start after a few minutes. So today in general our topic will be concentrated on the equation writing function in Mathematica with equal sign, and so there are two kind of equal sign, one is set and another is set delayed. So I'll discuss about that, and again then I will talk about the logical operators, and if time permits I will talk about some methods to solve and plot some differential equations. So this is week 3. Okay, so I will talk about the equal signs first. So in case of Mathematica, there are many different commands that involve the equal sign. But this sign does not just mean equals like it does in normal mathematics. So in Mathematica, there are two kind of way of writing this equal sign. The first one is set, and the second one is the set displayed. Okay, so the set defines an expression to be displayed upon execution, so it can be checked for errors, and the set displayed command defines an expression that must be manually displayed. So the solution or result of the command will not appear when you enter the equation for set displayed. Now there is another thing, that is the equal to sign, which is basically used to check that the defining an equation or for testing if an equality is true or not. So when you enter an equation in the form of fx equal to ax plus b, you use this command. The regular equal to is used to define assignments, while colon equal to is used to represent the left hand side in the form of right hand side when this is unevaluated. So normally one uses set or equal to define variables and set delayed to define function. Delayed to define function for which the computation of the right hand sign on a chain argument is natural operation. So now I will give example for this. For example, R1 equal to random real. So random real is basically randomly generated real number. Okay, so random real is 0.776887. Now I will do the same thing, but this time I will use set delayed random real R2. So here you can see that it is not giving us the value of R2, as when we call R2 only then the function will be evaluated, but here already R1 is assigned 0.776887. so let's just call them again R1 R2. So here you can see that the value of R1 is again same, because it is not being evaluated every time we write R1, but R2 is being evaluated and the value is 0.663968. Again we will write the same code, R1 comma R2. Sorry, here you can see the R1 value of R1 is same, but R2 is changing. It is happening because the R2 is being evaluated when it is using. When we are using R2 only then this thing is using, and the random real command is being executed, and that's why we are getting different result. So at input line 3 R2 is evaluated once, then in input line 4 R2 is evaluated again. That's why you get different value for R2 at different time, but R1 is always fixed because already we have assigned the value R1 for 0.776887. Okay, so now R1, R2, R3. So R1 is always fixed, R2 is this, R3 is this, and again the same thing is happening because we are running the same code. Okay, so now I will go into the logical operators. So now I will talk about the logical operators. Okay, so as many other languages, mathematics has several built-in logical operators. We will only consider logical and or in the and not. So basically we will talk about and, not sorry not or. These three logical operators we will only see. We will also see the logical operator if. So the if has if operator. So if test operation 1 comma operation 2. So this is the syntax for if. Now let's say if okay, so if r1 equal to 0, then we'll do execute r2, and if it is not, then we'll execute r2 plus 1, and we have executed r2 plus 1, and this is 1.56442. This is how the if statement is passed. Now then we will have the for loop. For I equal to 1 comma I less than 5 comma I plus plus comma print I. So here basically we are starting from I equal to 1. It will go up to I less than equal to 5, and it will execute I plus plus, and then it will print I. So we'll just enter. So yeah, so here you can see this is it, 1 2 3 4. So for when I equal to 1, it is I less than 5, that's why it is executed I plus plus and printed the I, and due to the I plus plus it became I equal to 2. It is again I less than 5, so it prints I, then again I plus plus, so it means that it is I equal to 3, print I, so we see 3, then we see 4. Now there is another way of writing this. I equal to 1 semicolon while I less than equal to 5 comma print I plus plus. There are some problems. Yeah, so this is the use of while loop. So we started from setting I equal to 1, but while we are checking I less than equal to 5, we are executing this command, print I plus plus.
So now you can see 1 in the range, 2 in the range, 3 in the range, 4 in the range, 5 in the range. That's how you use while. So if one needs to place several operators in the body of the loop, one can do so by just separating them with a semicolon. The same comment applies to the while loop. So this is basically a way of using the while loop, and this is the way of using if loop, and this is for loop. Here you can see this is we are using for loop. So this is we are executing two commands when I less than equal to 5, print I and print in the range. Okay, now we will see another loop where this is right or while loop. Now here another loop is to loop. Okay, so for do we will write the statement inside the print I okay, so the difference between for, while and do is for is when we check first the I is less than equal to 5 or not, then we execute the thing, and in while we continuously check that for I less than equal to 5 and we execute the command that is necessary. Now in do we don't check it, we just first write whatever we want to execute and then we write the range. So here do print I from 1 to 5. Okay, so in general most mathematical built-in functions do not introduce side effects since they operate on a copy of the given expression. In for and while loops, however, the index variable will keep the final value that they had when the loop terminated as a global value. It is good practice to localize all loop variables inside one of the scoping constructs available in the file. Okay, so a I to the power 2 do print a I 1 to 5. Okay, so we have printed the a I square, that is 1 to 5. I'll just let this 10. Now we have the square 1 2 4 9 16 25 6. Yeah, now it looks better using do loop. Now there are commands like break and continue. Okay, so I equal to 1, do print so this is the print. And now if I plus plus is greater than 3, then it will break the loop. So basically it should print 4x. Yeah, it has printed x. Okay, so if there is a loop is going on, and if you want to break the loop due to some condition, then you can just write if the condition and then break. Okay, now do print yeah, so here we have used the do loop, and the statement the command we have executed, that is print x. Now if I plus plus is greater than 3, that is if I is greater than basically I is 4, then it will return I. Okay, so now I equal to 1, I equal to 2, equal to 3, equal to 4, and then it will return I, so that is 5. Now again there is a way to write this: catch loop if I greater than 10, throw I want 20. There. Now we can use something like this. time Sn equal to 0 semicolon do Sn equal to Sn plus I comma 1 0 0 0 0. So 100,000. So now this is basically summing I for 100,000. So let's do that for 5. So this takes only 0, but when we increase, so this is basically summing all the numbers from 0 1 2 3 4 5. So not 0 1 2 1 2 3 4 5, so it is 15. Now I'll write this 100. So it is taking 0.0625 second. So summing up to 10 million is a little troublesome, and it is taking 5.9685 second. Now we will write this again in a different way. Timing apply plus range 1 0 0 0 0 0. So it is taking only 1.6 second, whereas do loop was taking 5.968. Okay, again we can do something like Sn equal to x comma 2 Sn equal to Sn plus I comma I comma n comma n. So it is like a compilation and then using module. So it is a complex way of writing this, but it is taking much less amount of time, and it is giving you the result in 0.171875 second. Okay, now I will go to another thing, that is the brackets. So Mathematica utilizes Four different types of brackets are used in Mathematica. One is parenthesis, single square brackets, double squared brackets, and the curly braces. So each different brackets has a different meaning and purpose. For example, this is parenthesis for grouping, then if so this is single square bracket, which is square brackets for functions a, b, c, is curly braces for list, and double square brackets for double brackets for indexing. So parentheses are used to change the priority of or precedence of different operators like in other programming languages. Also to group together a block of operators which we want to be considered as a single composite operator. Curly braces always mean a list. They are equivalent to a literal command list. Clear A, B, so curly braces always means a list. And here A list, A, B, C. So A is a list of the is a list where the elements are A, B, and C. Now we will use the indexing. So A of 2 is B. A of 1 is A. Okay, so these are the uses of the brackets. Now I will go to the main Mathematica thing. Yes, so now is a function defined by h of x, that is x cube. Now I'll write h of 2, that is 8. Now h of y equal to 7, and h of 3y equal to 27 y cube. So this doesn't mean anything. Okay, so this is the way you define a function. Now we'll use this desolve to solve some ODEs. yt. So this is the differential equation, y dash t plus 2yt equal to 3 e to the power t. So this is the dependent variable, this is the dependent variable, and this is the independent variable. Now the solution is yt e to the power t plus e to the power minus 2t c1. Yt equal to 3 exp p y0 equal to 3 . So this is the solution for this differential equation, y dash t plus 2yt equal to 3xt. But here there is a initial value, that is we have y0, y of 0, I mean y at t equal to 0 is 3. So this is the arbitrary, this is the general solution for this differential equation, and this is a particular solution for this initial value. Okay. So this is another solution of the differential equation, and so here you can see this is the solution. So the solution is getting changed due to the value of y at t equal to 0. So here it was 3, it was 2, so you can see the change here. Now we will use the manipulate plot e plus minus 2t So this is not working for some reason. All for resolve y dash t minus 2y t equal to 4 cos 4 cos t minus 8 sin t. So this is the solution for the this particular differential equation, that is yt is 3 e to the power 2t plus 4 sin t. So this is the solution for y dash x equal to x square minus 4x plus 3 minus 6 e to the power x. Okay. Okay. So this is the blue line where there is a coefficient a. This is the particular solution for the boundary value when t equal to 0, y equal to 3, and this is the solution for t equal to 0, y equal to 2. So here we are changing the value of a, and we can see that at certain point this blue line is matching with the green, and then the yellow. So we can say that this is the general solution for this particular equation, but these two are particular solution for this particular equation.
So this is a very simple equation, that is the acceleration is proportional to the negative of the g. So basically it is a so we are throwing something upwards in perpendicular direction, and that's why we have this kind of equation. So that's why the acceleration is minus g. So now the initial velocity is v, that is given by 10. So we have this solution for the velocity. So the solve value y dash x So this is the dissolved value. So this is an alternative to the dissolved value, and now we have the equation y, the solution for y dash x plus yx equal to a sin x, where the initial value is given by y equal to 0 at x equal to 0, and this is the solution. Anyway, so now we will plot this. Plot the table sol x and this is the solution for different value of I, or different value of a. Now again use this table to solve 6. So solve 6 was basically this equation where the a particular thing is thrown upward in the perpendicularly upward direction. Now we will just evaluate the value. Solve 6 e 0 to 10. So at 0 the velocity is 10, at 1 it is velocity is 0.2, at 2 its velocity is minus 9.6, and considering that the fact that it is not hitting the ground, the at the 3 seconds the velocity is minus 19.4, and so on. Now we can do the same thing with the displacement, and here in the from this equation we already know the instantaneous velocity, that is 10 minus 9.8 t. So we can use that and write solve 7 is b solve s t minus 9.8 t plus 10
is 0 equal to 3. Okay, so this is the equation. So the velocity, that is the first different derivative of the displacement. So displacement is given by s, so the first derivative of it is equal to minus 9.80 plus 10, and the initial displacement when the t equal to 0 is 3. So this is the displacement, is 3 plus 10t minus 4.90 square. Now we can do the same thing. Solve 7 t 0 to 10. So at 0 the displacement is 3, at 1 second the displacement 8.1, then again it is going downward basically. So at 2 second the displacement 3.4, and at 3 second it is minus 11.1. So by here the thing should hit the ground. Okay, now just try to see if we can solve it like this. Okay, first do the easy problems. We solve y x y dash x equal to 7 star y x. So this is the differential equation. Y dash s equal to 7y square x cube, 4 by 7 x to the power 4 plus 4 1. X dash t equal to minus xt sine t. Initial value is x of 0 equal to 2. Now the dependent variable x of t, independent variable t. This is the solution for xt. Okay, so now we can check this. So this is the point of throw. So here is thrown and then the thing is falling like this, and at this point of time it is hitting the ground. So if it is started at 1000, then at around 10 seconds it will hit the ground. Okay. So this is the equation of damped oscillator. So x dash double dash t plus beta x dash t plus 1 naught square xt equal to 0. So this is the equation. Now we'll use a ND solver. ND solve. Okay, so this is the numerically solved result of this differential equation. Y dash x equal to yx cos x plus yx, while y0 equal to 1. Solution is for x to 30. We'll just use that. Okay, now we will plot that. Plot evaluate yx So evaluate will basically evaluate the value of y using this in s, and then it will s, and then it will plot up to x to x 0 to 30. So let's just run up to this point and see what happens. So evaluate is basically the interpolating function, so it is going to give this thing. Now plot evaluate y(x) s, comma x0 to 30, plot range all. Yeah, so this is the solution from 0 to 100. Now let's see if we use this, something like this. It did not know the value at this one, so that's why this is giving this kind of weird result. Okay, so this is the displacement plot, and this is the plot for the velocity. So the velocity is showing a straight line because its slope is constant, as it is experiencing a constant deceleration throughout its journey, and at this point it is crossing the zero value. So at around 1 second it is crossing the zero value. So at this point the particle or the pebble or whatever we have thrown is coming to at rest at in the air, and then it is starting its downward fall. Right. Your one is square root mean okay. So here we have generated a table of numbers. So the numbers are like the integer numbers 1 2 3 4 5 6 up to 100, and then we calculated the standard deviation of it using the formula, and then we have used the standard deviation command available in the Mathematica, and we found there is a difference. So the standard deviation we are getting using the formula is 28.8661, and the standard deviation from the package we are getting 29.0115. So the difference between these two are 0.145422. Now let's put some data, assign some data to A. 2.43, 3.5, 3.1, 3.25, 3.14, 0.12, 0.1, 0.15, 0.11, 0.2, 0.44, 66, 0.88, 3.74, 3.69, and then 2.5, 2.36, 0.7. Now mean of A. This is the mean. Now square root mean of A as one, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. Total 18 points are there. So this is the standard deviation 0.107606. Let's another number like 54 here. Oh, sorry, 54 should be here. Yeah. So this is the standard deviation. Now let's do some different thing, like A1 is 1, omega 1 is pi, pi 1 is pi by 3, A 2 is 1, omega 2, so 2 equal to pi phi 2 equal to 0. omega 1 G A2 cos omega 2 t plus phi 2 h t dash okay. Okay, so there G was 9.8 was assigned to G, that's why we are getting some problem. But now this is we defined some variable a1, omega 1, phi 1, a2, omega 2 and phi 2, and then we define some function f and g. So f is the f is basically a1 cos omega t plus omega 1 t plus phi 1, and g is a2 cos omega 2 plus phi 2. Now ht is multiplication of these two, ft and gt. T0 10 pi loss style, this is it. Now we'll do some parametric plot where f t comma g t 0 100 axis level f comma now let's do that again, and f1 t e11 cos omega 1 phi 1 this is phi 2 f1 t comma g1 t. Let u11 to 5
Mm, this I'm just trying. I'm not sure it will work or not. So just listen to. Looks like it is not working. So this is the plot of Visage's figure. So if you remember it, this is the plot of Visage's figure basically. Yeah. Again here we can add something.
So here you can see this is a different kind of thing happening here. Okay. So now table find x. So these are the prime number in first 20 prime numbers. So these are the prime numbers, first 100 prime numbers, which is gone up to 541. Now find fit percentage ax log b plus bx okay. So this is basically the we have fitted a line with this number of prime number, list of prime numbers. So this is ax log plus b plus cx. There are three fitting parameters a, b and c, and after using this find fit using percentage, so basically this percentage denotes the line before this comment. So here it is in the input line 134, so this percentage refers to the line output line 133. Okay, now after fitting we get a is 1.11183, b is 0.00435079, and c is 1.20662. Now we will list we plotted the prime numbers and the fit, and we get like this. So here we list plot percentage 133. So percentage 133 means it refers to the 133 output line. Plot style red, plot ax b plus c, ax log b plus cx. This is the value, and we get this. Now let's do another thing. Okay, so this is insanely large. So here you can see using this the value is changing a little bit, not a little bit, b is rechange, so this is a bad idea to use 10,000. Yeah, so using 1000 we get this. So you can see that A is 1.11919, here it is 1.11183, then B is changed to 0.0043570, it is changed to minus 0.87249, and C is 1.183 where it was 1.2. So you can see this is matching more or less, but the values are different. Now table AX log P plus So here this is a demonstration project. We have found the full form which I was wanting to show. So here you see this, the spring system. So the displacement of the spring is generating a simple harmonic motion, and if it is a piston it is also like same. So both of them are generating a simple harmonic motion, and so it helps to understand how to get the differential equation from simple harmonic motion by linking the vertical position of the moving object to a point A on a circle of radius r. Computing a second order derivative of y in the equation y r sin omega t gives the equation of motion y double dot equal to minus omega square y. Okay, now table ax log p plus cx percentage x comma 10 percentage 1 4. Yeah. So these are the values using this fit. Okay, now again define a variable data equal to table total table random random real comma n to in 100, 1000, 100. So these are the values. So this is basically it is generating a random real number, then it is doing the total, and then it is again generating a table. So this is the thing. Now again we will fit find fit a star x to the power b. So this is the value for a and b. Now again get back to the equal I have taught at the beginning of the class. So equal to cos x minus 1 divided by x to the power x. We have 2. So there is no output, but to see the output we have to print it, because only then it is getting the fx is being executed. Now g of x underscore equal to cos of x minus 1 . So this is giving the exact equation again. Now g of 2x plus 1, you can say this. So this x underscore is pronounced as x blank. Now in f of 1.5 is like this. Now there are lots of things we can do actually by For example, let's do this now. Okay, so this will give the date and time and the time zone, all these things. Also, Mathematica can provide some really interesting thing like sorry, okay, so yeah, again we can have this thing 1 by 3. So this is a cubic root function. So f of 27 basically 3. Okay, now again square equal to function x to the power 2 square 1 to n. Again we can define it like this, square 2 x blank now we'll use down values square because this is a special type of command in Mathematica that is not very necessary, but down values gives a list of transformation rules corresponding to all down values defined for the symbol f. So we did this, then here there is nothing defined, but in here it is defined, that is the hold pattern square to x is this one. Again so in map command you are using this one, but here the map command is changing a plus b c plus c to a square plus b square plus c square. Let's define a piecewise function, for example t blank p piecewise T 0 is less than 2. Now this is a t square when 0, the t is between 0 and 2, and 4 minus t when t is between 2 to 4. Okay. Now f of 2 is 2, because otherwise it is 2, so that's why there is no problem. But let's see at f 5 is 2.25, so basically this is for t square part. Now f of 3.5, it is 0.5 because it is coming in this part. Now we are doing this by one. Now we can do that like this: f as and at the rate 2, 1.5, 3.5, 4.5, and we can get all the values. Now find max value f of x comma x, which is 4. So this is a warning error, so we'll just quit that message and do this. Now we'll find minimum value, find min value f of x. This is the value. Minimum value for sin x, sin y. Again we can do the derivative of f of t. Okay, so this is the function t square 4 minus t 2. Here we will have 0 2t minus 1 0 in return. Now let's plot it. So this is the plot of this differentiation, and if we change that to so this is the piecewise this plot of the discontinuous function, and this is the plot of the. Let's plot another function, that is 1 t blank piecewise So this is the function. Now we'll plot lt1 plot f1 t comma comma 0 10 plot range full plot everything. So this is the plot basically. Okay. Okay, so this is the plot. Now again f of t blank piecewise so this is the function. Now we calculate f2 so on. Now we can calculate the limit of it. Limit f of x from x tends to 2 dx from below. This is one way, and another way is write it like that, and then direction is this one. Oh, sorry. Now again direction from above, and this is minus one. Here you can see this is 2. Okay, so today we have talked about a lot of things, different way of handling the function in Mathematica. So first is the using of the equal sign, that is the double equal to, set delete, which is colon equal to, and the normal equal to. So we talked about the differences, then we talked about the logical operators. So we do not talk about the and, nor, or. We have talked about only the loop. We will talk later about the and, not, or. So basically this and, not, or these commands will be included in these conditions, but we can use multiple conditions. Okay, so now we have talked about the if, for, while, then do loop, then break and break, return is the continue. Yes, then we calculate the timing of a loop using this timing command. Then there is the difference between the parentheses or brackets, that is this parentheses for grouping, square bracket for function, curly braces for list, and double square bracket for indexing. Then we use dissolve and plot it and generated the okay, so we generated these things, but here we can use another thing, that is the y dash 0 equal to 1, y So this is the second order differential equation solution. But now the first thing is, this is a general solution here, but this is a particular solution of the equation basically, with different boundary value, and we plotted example of this, and then we can see that by changing this blue is matching with the two solution at different points. So by changing this A, we are getting this one or that one. Now this is another example of desolve. Then we solve the equation for the particle that is thrown in upwards perpendicularly from the ground, or from a certain height from the ground. We calculated the value of the so at different point of time we have calculated the value, and then we have plotted it here and did some other solution using the table. Then we have talked about the parametric plot, use the manipulate and so on. So this is it for today, and we'll again meet in the next week at the same time on Tuesday, and talk about many more problems in this problem solving session. Thanks for joining.